to this lecture of hyperbolic geometry. In this lecture, we'll learn about inner product on upper half plane with respect to hyperbolic metric. And we'll also learn about the angle between two geodesics meeting at a point. So let us begin. In order to define the inner product, we should have some vector space. So first, we'll be defining the tangent space of this upper half plane, and that will be a vector space. So tangent space of this upper half plane, so this will be isomorphic to your R2 as a vector space. So first, let me just give the definition of this tangent space of this upper half plane. So let us pick a point P from this upper half plane. And so what is my tangent space of this upper half plane at the point P? It is the following. So TPH2, so this notation stands for the tangent space of this upper half plane at P. Okay, so what is the space? So this is the set of all this gamma dot 0. So where this gamma is a differentiable path in H2 such that gamma 0 is equal to your P. So you take the collection of all these velocity vectors with respect to the differential path passing through P. So this will be a vector space. So note that this gamma dot 0, so this lie in R2. Okay, so therefore this TPH2, so this is a subset of this R2. And now if I take any vector, so let B belongs to your R2. And if I consider this path, so let gamma T equals to TV plus P. So here this gamma 0 is equal to your P. And note that there exists epsilon greater than 0 such that, so this image of gamma T, so that is TP plus P belongs to your H2. So for all T in this interval minus epsilon to epsilon. So if I take this path gamma T equals to TB plus P, so this is certainly in R2. So this is in H2. So if T belongs to your this interval minus epsilon to epsilon. And also note that this is a differentiable path. So and gamma dot 0 is nothing but your P. Okay, so this implies that, so this B, it belongs to your TP of H2. So therefore, so this tangent space of this upper half plane is exactly equal to your R2. So therefore, so this tangent space of this upper half plane, it is a vector space. And now we are going to define an inner product on this tangent space. So we'll call it to be inner product on this upper half plane. So this inner product, so will be different from this Euclidean inner product. And this inner product will give the hyperbolic metric. So let us take a point. So let P belongs to your H2 and consider the tangent space of, consider the tangent space of H2 at the point P. And now let us take, so, two vectors in the tangent space. Okay, so now note that, so this tangent space, so this is your R2. And again, you can take it as also the set of complex numbers. So this V, so either it can be denoted like xy, or it is same thing as your x plus iy. So let us take this B to be x1, y1, and let us take W to be your x2, y2. So the inner product is on this tangent space is defined as follows. So the inner product is defined to be, so this is my definition. So you first take this x1, x2 plus y1, y2. So this is the Euclidean inner product. And now you divide it by the imaginary part of this P square. So you take the square of this imaginary part of this P. The Euclidean inner product between B and W is divided by the imaginary part of this point, square of the imaginary point of this point P. So this is my Euclidean inner product divided by the square of imaginary part of P. Yeah. So this is the Euclidean inner product. Okay. So I have defined this inner product. And now what do you mean by norm of a vector? So norm of a vector, it is denoted by the symbol. So this is equal to, as for the definition, so this is root over inner product of B and B. And now I'll define, so what do you mean by angle between these two tangent vectors? So this inner product, so what I have defined, so this is different from the Euclidean inner product because I have scaled the Euclidean inner product by the square of the imaginary part of this point P. So now, so what do you mean by angle between B and W? So this is defined to be, so this is my notation. So this is defined to be cos inverse of inner product of this VW divided by norm V times norm of W. Okay, so again, so why this cos inverse is defined here? So you can check by this Cauchy-Schwarz inequality. So by Cauchy-Schwarz inequality, so mod of this inner product is less than equals to norm B multiplied by norm W. So this implies that, so -1 is less than equals to the inner product divided by the multiplication of these two norms. And this, yeah, this thing is again less than equals to 1. So therefore, cos inverse of this thing, it makes sense. So therefore, I have defined the angle between two vectors. So now what will prove that, so if I take an isometry of this upper half plane, so norm of B is equal to the norm of dt of B. So dt is the differential of this map T. Okay. So first of all, let us observe this thing. So if I take, so this is just an observation. So let alpha be a piecewise differentiable path, and let alpha t is equal to your xt plus iyt. So then length of alpha, so length of alpha, so this is equal to your this integration. So integration 0 to 1 root over dx dt whole square plus dy dt whole square divided by yt times dt. And also note that if I take alpha prime t, so this is equal to your x prime t plus I y prime t. So norm of this alpha prime t, so this norm I am taking with respect to this hyperbolic inner product. So this is equal to root over. So this norm I am taking at the point alpha t. So this hyperbolic inner product is what? So first you take the Euclidean inner product. So this is the Euclidean inner product at the point alpha t, and divide it by the imaginary square of the imaginary part of this alpha t, which is nothing but yt whole square. So this is equal to, so root over, so alpha prime t is your x prime t plus iy prime t. So then in the numerator, so what we'll have here, it is so square of the norm of alpha prime t, and that norm is Euclidean norm. So which is nothing but dx dt square plus dy dt square. So that is your this x prime t square plus y prime t square divided by this yt. Okay. So length of, so alpha is equal to your zero to one norm of alpha prime t dt. Okay, so now if I take an isometry, so let T be an isometry of this upper half plane, and let us take Tz to be equal to your u plus ib, where the z is equal to x plus iy. U, it is a function of x and y, and b, it is also a function of x and y. So because T is an isometry, see, so this formula will be preserved. So this we have seen earlier. So this will be equal to your, so root over dx dt square plus dy dt square divided by yt. So this will be equal to your root over du dt square plus dv dt square divided by vt. So this implies that, so norm of alpha prime t is equal to your norm of t compose alpha prime t. And now if I take So, okay. So if b is equal to your alpha dot 0 for some differentiable path alpha, so norm of b, so this will be equal to your norm of this alpha dot 0. So, okay, so here let me take p equals to your alpha 0. So, norm I am taking at the point p. So in the above case, it will be the left side will be norm of alpha prime t at the point alpha t, and this is equals to norm of decompose alpha prime t at the point decompose alpha t. So now this t, it is a map from this upper half plane to upper half plane. So this differential of t, so it is a map from this tangent space of this upper half plane at the point P to the tangent space at the point TP of this upper half plane. This differential dTP of P, so this is nothing but equal to your decompose this alpha prime 0. So therefore, so this norm of this P at the point P, so this will be equal to norm of this dTP of P. So this follows from this equation. So in this equation star, if I put t equals to 0, so then we get this equation. So this, let me write down this thing. So dTP is called the differential of t at the point P. Okay. So now let us define. So what do you mean by angle between geodesics? If I take two vectors, so we already have defined an angle. So if I now take two geodesics intersecting at a point, so at that intersecting point, so we'll get two tangent vectors corresponding to those two geodesics. So the angle between those vectors, tangent vectors, will be called to be the angle between those two geodesics. So we define an angle between two geodesics in the upper half plane intersection point P belongs to H2 as the angle between their tangent vectors in the tangent space. For instance, so if I take two geodesics in this upper half plane, so let me first draw this upper half plane. So this is my upper half plane. Now if I take two geodesics, so this is a part of a geodesic. And if I take another geodesic like this, and now we can have tangent vectors with respect to this blue geodesic, and we have also this tangent vector with respect to this red geodesic. Suppose this is my V1 and my V2. Okay, so now note that, so this two V1 and V2, so these are vectors in R2. So we have the notion of angle coming from this hyperbolic inner product, and also have the notion of angle between coming from this Euclidean inner product. Okay. So what is the, so if I take this two geodesics to be gamma 1 and gamma 2, so they are intersecting at point P. So angle between gamma 1 and gamma 2 at the point P. So this is defined to be the angle of these two vectors, P1 and P2. So which is nothing but equal to your cos inverse. So this is my inner product, hyperbolic inner product, divided by norm of this P multiplied by norm of this W. Okay. So now if I take the Euclidean inner product, okay, so let us observe this thing. So this hyperbolic inner product, so this is my hyperbolic inner product. So this by definition, so it is equal to the Euclidean inner product divided by the imaginary part of P and take the square of that thing. So norm of this, yeah. So if I take the norm of this B and take the square, so this will be this hyperbolic inner product. So this will be equal to again this thing. So you take the Euclidean inner product of this B and B and again divide it by the square of this imaginary part of this P. So this is again equal to, so this is my Euclidean norm, and take the square divided by this. Okay, so what we have here, so norm of this P with respect to this hyperbolic inner product is equal to norm of the B with respect to Euclidean inner product divided by imaginary part of this, square of the imaginary part of this P. Okay, so now, so this thing is same as, so if you take the Euclidean inner product, divide it with this square of this imaginary part of this P, and norm of P is nothing but you take the Euclidean norm, divide it by imaginary part of P, multiply it with Euclidean inner product of this W divided by the imaginary part of this P. So this will be equal to Euclidean inner product of this P and W divided by this Euclidean norm of this P multiplied with the Euclidean norm of this W. So this is basically gives you the, so this thing right hand side, it basically it gives you the angle between this B and W in the Euclidean sense. So if I take this to be your X, so cos inverse X is the Euclidean angle between P and W. Okay, so because of this formula, so therefore what we have proved that, so the hyperbolic angle between the vectors V and W is same as the Euclidean angle. Okay. So also note that, so we have proved that the isometries of this upper half plane, so they are conformal with respect to this Euclidean angle. And again, so this will also preserves the hyperbolic angle. So therefore, this isometry of this upper half plane, so they are also conformal with respect to the hyperbolic angles. Okay, so I'll stop here. So in the next class, we'll be proving that area of a triangle is equal to pi minus sum of the angles on each vertices of the triangles.